Thank you very much, Richard. And first of all, I want to thank the organizers for making sure a smooth online conference of this many people. So as introduced, I'm going to talk about Hamiltonian simulation in the low energy subspace, which is a joint work with Rolando Somma. And as a note, he just messaged me that he is in the Slack chat room. So if you guys have any questions, you can also ask there. And you know, it's a luxury today that we have two speakers who's able to answer the questions. And I'm assuming that you are here in this room instead of the other two rooms. You are interested in quantum algorithms and quantum simulation. So I strongly advise you guys to check the tutorial by Andrew Charles that's given on Sunday, if you haven't already. Okay. Okay, sorry. Okay, yeah. So what do we mean by Hamiltonian simulation? The problem is as follows. We are given a Hamiltonian H, and the goal of the problem is to simulate e to the minus IHT, this time evolution operator. And there has been a lot of work on this topic. One of them is coming from way past, from Trotter, and that has been made much clearer and precise by Suzuki. And then in the past 10 years, there has been two more methods, which can be called Taylor series method and quantum signal processing. So as I said, it's a well-developed field with many important works. So I will not try to capture even the milestones here. And for that, you can check the tutorial given by Andrew. So if we look at the important physical scenarios for which we want to study these problems, you know, from a more physics perspective, we actually see that we are, in most of the cases, we are interested in the low energy simulation or low energy physics. For example, if you want to simulate quantum field theories, the interesting and reliable physics usually takes place in the low energy subspace, which is usually way below the energy cutoff of the regularized theory. There's this, you know, naming called high energy physics to the whole field, which studies quantum field theories and other type of theories, but it's an unfortunate misnaming that's coming from the past. What you really have there is that you regularize your theory. Say you have a lattice regularization, and the reliable physics actually is happening much below the cutoff 1/A. And furthermore, quantum field theories with bosonic degrees of freedoms suffer from infinite norm problem, simply due to the fact that you can in principle have infinitely many bosons. But there as well, the most interesting physics or interesting physical problems are actually those where you have either finite number of bosons or some certain number of bosons. Furthermore, you know, a closely related problem is simulating many-body quantum dynamics. And for example, there's this general method called adiabatic evolution. And that also usually takes, that fully takes place in the low energy subspace during the adiabatic evolution. And it's important to understand the complexity requirements of, of simulating this operator, given the fact that we are actually operating in the low energy subspace. And in general, this is really believed to be one of the main and meaningful applications of quantum computers. So it is important to explore the possible physical scenarios and how to apply them in quantum computers, and what are the complexities that we would expect for these kind of problems if you want to simulate them in a quantum computer. So as I'm motivated, we are going to look at this Hamiltonian simulation problem, given the restriction that the input state psi lives in a low energy subspace. And during the talk, we are going to mainly be interested in the product formulas. And we expect an improvement in the performance if and when during the evolution under the product formula. So when we are simulating this e to the minus IHT via a product formula, if during that evolution, we are not exploring the high energy subspace, then we expect that we get less complexity, and we will require less resources from the quantum computer. This is due to the fact that, as we will see, the complexity of the product formulas comes from the fact that the error bands scale with the norm of the Hamiltonian. But if we are never exploring the high energy subspace, if we are never touching the high energy states, then we will get an improvement by basically given by the sort of an effective norm that depends on the low energy subspace. Okay. So before getting into the details, let's first quickly remind ourselves, what do we mean by simulation? Simulation means that eventually we want to find a quantum circuit W that approximates the time evolution operator e to the minus IHT. And for example, in this diagram, we have 1, 2, 3, 4, 5, 6, 7, 8 degrees of freedoms. They can be spins, they can be other type of degrees of freedoms. And there are quantum gates available to us that are, for example, coupling these two spins, or the third and the fourth, and so on. And eventually, we count the number of gates that we use in this quantum circuit that is approximating this operator. And this number of gates is our complexity. Note that this is, I'm not really distinguishing between different type of gates. So for me, every type of gate is of equal complexity. This is why we are simply counting these gates. And the main goal is to find the least possible number of gates. Well, the main goal is to find the quantum circuit W with the least possible number of gates, such that the desired accuracy is met for approximating the operator e to the minus IHT. More precisely, we want to find the quantum circuit W with the smallest number of gates. For example, linear or better polylogarithmic in the total evolution time t, total number of degrees of freedoms n, and inverse approximation error 1 over epsilon. Okay, so let's get back to our result. And right at this moment, you may be thinking that, well, you think that you will get an improvement, and maybe that's just your opinion, like show me some evidence. If you're thinking like that, here is a small scale simulation of Heisenberg model on 12 sides with this geometry. And what we observe is that if you look at the error between the first order product formula and the correct time evolution e to the minus IHS, we see that the worst case error scales much worse than the error that we would get if we start from the low energy eigenstates. This is the 50th, this is the 150th, this is the 200 eigenstate, excited state of this model. And the same happens for the second order product formula as well. So then what, right? I mean, we have the small scale simulation that clearly shows us the result that we expect, but there are problems with this in a way that we should not, extrapolate the conclusions to larger and larger systems. So the reasons why we bother going beyond the small scale simulations are as follows. An advantage in a small scale simulation, such as 12 sites, 15 sites, 20 sites, doesn't really matter, it does not really guarantee anything about any larger scale simulation, because the goal eventually is to simulate the time evolution or the dynamics for larger and larger system sizes. And furthermore, a large scale simulation is not possible without a quantum computer. And unfortunately, we do not have any yet. So we are really forced to study this problem with our analytical techniques. And even if we had a quantum computer, when we do a simulation, we always do it for a specific Hamiltonian. So today you are interested in Heisenberg model. Tomorrow you are interested in another model. Next day you change your mind and you are interested in some other model. I mean, sure, with a quantum computer, we can try all of these and try to see the performance of the product formulas in the low energy subspace or other simulation methods. But what we claim is more stronger. We claim that the low energy simulation is less costly for a broad class of models. So this is why we wanted to prove these claims for in general Hamiltonian systems. So there are at least two ways to approach this problem. And the first approach is something that is closer to the hearts of condensed matter and high energy physicists. What you want to do is basically, in this approach, is that you want to find a low energy effective Hamiltonian such that the dynamics in the low energy subspace is faithful to the original dynamics. But there are problems about that, because the first problem is that the Hamiltonian gets non-local. So this is going to get much more costly if you are, for example, trying to implement a product formula. And furthermore, there is no general and efficient procedure for finding these effective Hamiltonians, let alone non-perturbative regimes or the Hamiltonians at the non-perturbative regime. Even at the perturbative regime, we fail to find general and efficient procedures to find these low energy effective Hamiltonians. Of course, if you're a high energy physicist, I'm sure you are doing this in a daily basis, but you are applying these methods, whatever method you have in for specific models, and somehow, there's a lack of a general method to approach this problem. So given these restrictions, we tried another approach. Our way of treating the low energy simulation problem is, in my mind, much simpler. We do not really change anything. We apply the same product formula with the original Hamiltonian. And we study how faithful this original product formula evolution to an exact low energy evolution. I mean, there are also problems here. The product formula, the evolution provided by the product formula makes the state leak towards the high energies. So there's some unfaithfulness there to the original evolution. And also, locality is harder to exploit. So we will see that in the most advanced Hamiltonian simulation methods, you can exploit locality and can improve the complexity bounds near to optimal. So in our method, at least as of now, we do not know how to do that. But at the end, things work out just fine so that we can prove a polynomial improvement compared to the best known models. Best known simulation methods. Okay, so I guess this much motivation and summarizing the ways of approaching the problem is enough. So let us get into the description of the product formulas first. So what we do in an application of a product formula, we first decompose the Hamiltonian into Hamiltonian terms, say sum over L, HL. So each of these Hamiltonian terms is already a sum of more basic elementary Hamiltonian terms. And a simple case is, for example, you can decompose the H. If it's a two local Hamiltonian with degree 2, you can decompose it by H even plus H odd. And ideally, we want to choose this decomposition in such a way that the Hamiltonian terms in each of the terms HL are commuting. This is not necessary, but it just comes handy, because if that happens, when you are applying your product formula, you can just apply one type of partial evolution with a circuit of depth 1. And a p-th order product formula implements a product of these Hamiltonian terms, these evolution by the partial Hamiltonian terms for time s, let's say, with a particular sequence of HLs. It looks like that. So you, for example, evolve with partial Hamiltonian term HL1 for time S1, HL2 by time S2, and so on. And you cleverly come up with a formula like WPS, and people already did that, in such a way that you are faithful to the original time evolution, e to the minus IHS, up to an error that scales with p to the first power of time s. And it turns out that you get a multiplicative factor that goes like the p to the first power of the norm of the Hamiltonian terms HL. And eventually, when you want to simulate the full time evolution for time t, you repeat this basic step, this WPS r times, which is t over s. And in the worst case scenario, if you just apply the triangle inequality, you will get an error that scales r times the error that you get from a basic Trotter step. And r is known as the Trotter number, and it is going to be our complexity measure. So we want to pick s in such a way that r is optimal, r is minimal eventually. Okay, so this is the general story of product formulas. And what we do is summarized as follows. So different from the general product formulas, we say we want to impose the condition that our initial state is supported in a low energy subspace that is quantified by delta. So this is the projector onto the low energy subspace that has energies less than delta. And what we expect and what we find is that instead of the error being scaled as p to the first power of the norm of the Hamiltonian, it scales as an effective norm. So this HL, the norm of the HL, will be replaced by delta prime. So you may ask, why isn't this simply delta? It's because this product formula is, each time we apply a partial Hamiltonian evolution, we are leaking out of the low energy subspace. It's simply due to the fact that the eigenvalues of the partial Hamiltonian terms do not match with the eigenvalues of the original Hamiltonian. And eventually, the total error will get replaced by r times the error that we get from the individual Trotter step. So, okay. Great. So before getting into the details, I want to show the results for low order product formulas. So here you see the product formulas of order 1, 2, and 3. Tau is j times t, where t is the evolution time and big J is the strength of the local Hamiltonian terms. And here we assume k local Hamiltonians with degree d, and we assume that our low energy subspace is quantified by energies delta, and we assume all of these to be order 1. More general results, you can read it in our paper. So what we see is that at the first order product formula, we get a definitive improvement compared to the best known previous results by product formulas. When the order of the product formula gets higher and higher, we lose the improvement at some certain range of the parameters, but we always have a range of parameter of, say tau and n, where we always have an improvement. So this is due to the subtle fact that they are able to exploit locality in their results, but we are not. But we are heavily playing on the low energy condition. Okay. So in the most general sense, the structure of the Hamiltonian is given as follows. It's a k-local Hamiltonian acting on n spins or n degrees of freedoms. We assume that the Hamiltonians are positive and they are, the strength of the Hamiltonian terms is upper bounded by J. In the product formula, we group the Hamiltonian terms into big L terms. This is, completely up to you. And then H is degree D. The degree of the Hamiltonian means that every spin is included in at most D many Hamiltonian terms. So this is, I don't want to proceed in the rest of the talks with this complicated setup. So let's just make things simple. Let's just assume that we have a nearest neighbor Hamiltonian. Say Hamiltonian is a sum of two local terms, and everything is the same. And when it's also degree 2, you can decompose it in this way, in such a way that the terms in H even and the terms in H odd are commuting, within that set. And what, our main result, the main ingredient to get our result is that, the difference between the product formula evolution and the exact time evolution for time s, the error between them is scaling with delta prime times s to the power p plus 1. And this delta prime is what we call an effective norm, depends on delta and the amount of time that you evolve your system as. So it scales like that. And eventually, you should note that this S is tried to be chosen as large as possible so that, this term, which is kind of an artifact, does not cause any problem. And then the total error is given by this amount. This is another slide where, I explicitly put the expression R that depends on, system size, the total evolution time, and the error. And how do we prove our result? Well, we prove our result by this ingredient that we use, which basically says that if we start from the low energy subspace that has energies less than lambda, we are leaking towards the higher energy states that has energy higher than lambda prime by at most this amount. Note that there's an exponential suppression between the differences of energies, lambda prime and lambda. So that's a good thing. We are not really going towards higher and higher energies, but then this exponential suppression gets weakened by this term, which basically scales exponentially with the system size and the time evolution s. This is a result that follows by a previous result by Arad, Kuwahara, and Landau. Let me quickly go through the derivation. I'm not going to get into the details, but the main thing that we do is that we observe that there are two types of errors that is coming to the product formula evolution, assuming that we start from the low energy subspace. Our state is supported here. The first error is coming from the leakage to higher energy subspaces. So that's, product formula is leaking us towards energies higher than delta. And then the other error is coming from the commutators in the product formula written for the time evolution with effective operators defined by this delta prime. So we have two types of errors, that is written in this form. Or more visually, we have a leakage error that is leaking us from low energy subspace to higher energy subspaces, and a low norm Trotter error or effective norm Trotter error that is coming from the errors happening within the subspace less than delta prime. And eventually, we prove the result by making this epsilon and delta to be at the same order. which is basically, optimizing this quantity delta prime in such a way that this error, the leakage error, is of the same order of the low norm trotter error. Okay, I'm running out of time, so I'm skipping the details of the derivation. But as I said, it's basically using this exponential suppression for the leakage and making this low norm trotter error to be at the same order of the leakage error. This is again the results that we already saw. So to summarize, we show that product formulas complexity are improved in some cases, especially at small t, small p, at small order trotter formulas, and for large t and or small error. If we are given the promise that the input state is a low energy state, as I already pointed out, the work by Charles et al. And many others, they make use of locality in the general case, and this gives them a lot of leverage. And as I said, it's an open problem to use these two things, two ingredients, having a local Hamiltonian and operating at the low energy subspace at the same time to improve our results more. So that's an interesting path. Okay, I'm just skipping this until important applications. Yeah. So as I said, our work is important for quantum field theories, and it fully applies for frustration-free systems. And it also is going to be important for the adiabatic evolution. And furthermore, similar ideas has already been applied for other type of subspaces, where, for example, in this work, they looked at gauge theories or symmetries of the system, where you can improve the simulation method by effectively projecting onto the relevant subspace. And then there's a recent work as well, which you will actually hear in the QIP program on Friday, where they kind of looked at a subcase of this problem and they analyzed that problem for electronic systems. I think that's all for now from my side. And if you guys have any questions, I'm happy to take it here and at the roundtable or at the chat. Thank you.
Thank you very much, Burak. That was very interesting. We have a little bit of time for questions. Sirui Lu asks, does this method have implications for simulating many body localized systems?
I believe so. I'm not an expert in many body localized systems, but if the problem that you are simulating is happening at the low energy subspace, and if you have this kind of Hamiltonian structure there, which I believe that is the case, then you need to go and check how local that Hamiltonian is and what's the degree of that Hamiltonian, and eventually compare those results with those results that use locality, and eventually I believe it's going to be the case where you will get a much when you simulate your system really in the quantum computer, obviously you're not going to see any of these upper bounds, right? You're going to see basically an error term,
okay.
trotter error term, and then that's going to be much lower than all these upper bounds that you observe.
Okay, thank you. We have another question, Martin Kleisch, which is how tight are your bounds? Now, we're kind of at 1:30, so if you have a one-sentence answer now, you could give it. Otherwise, we could defer discussion of that in the chat room.
Yeah, so as far as the proof method goes, we believe it's as tight as possible. Okay. We observe that there are worst cases that saturate some of the bounds. But maybe
let's leave it at that.
Yeah, let's.
Because I want to just keep on.
Yeah, okay.
So thank you very much. Sorry, I just want to.
No, that's
Good.
all.